Hello everybody and welcome to the 11th lecture of MHM 420 780 MUA 781. If you recall, during the last session, at the end of the last session, I said that we talked about condensation or boiling and boiling, but we might mix different concepts of heat transfer into each other to ask you like one question. Based on my previous experience, sometimes it's a little bit strange for students. So I'm going to solve one example today to show you what I meant by saying that combining different concepts. But you are a little bit familiar with this with it before. Just think about it. Like if you look at that, look at your textbook, you see that when we are talking about convection heat transfer, we were just focused on convection heat transfer. We didn't talk about radiation at all when we talked about convection heat transfer, not in this course, but in, let's say, MTV. Again, after that, we started about radiation heat transfer. We talked about radiation heat transfer, and at the end of that section, we said that, oh, it's not just about radiation. We might have convection heat transfer simultaneously. So we have convection, we have radiation. So and you can't neglect any of them in some cases, so you need to calculate both of them. In this case, let's solve one example and see what I meant by combining different concepts into condensation or boiling. So you see here that it's looks very simple, very simple, like a figure, very small explanation. So it should be very easy to calculate. I think it is easy, but needs a little bit of a special attention. So let's first go directly to what the question is asking us. At the end is asking us, determine the rate of condensation of steam. That's fine, Q dot we know, Q dot of condensation. But it's also asking about the average overall heat transfer coefficient. Okay, average overall heat transfer coefficient. If I'm not mistaken, that's a concept that we learned when during the can you remember that? Help me. Yes, exactly, heat exchangers. Okay, so we talked about it and we know how to calculate the overall heat transfer coefficient. We know about the correlation. We talked about it during the MTV, not me, but with your lecture. Even though during this course, at the end of this course, we are going to again talk about the heat exchanger and its concept associated with it, concepts associated with heat exchangers. But here it's a very good example. So first you start with condensation, but after that immediately the question is asking you to find the overall heat transfer coefficient. Okay, so let's start to solve it together and see what we can do. So the first approach is, okay, condensation, so easy. We just like start. First we get the saturation temperature. After that we read the HFG and rho V at saturation temperature, the list of properties at film temperature from the table. So looks easy. So let's start then. Okay, let's start. So we said that, okay, steam at 40 degrees condensate, so Tsat is 40. We go to the right table and we, as I said, we read HFG and rho V from the table. I'm not going to give you the number of the table, but you need to find it. Table number at 40 degrees. If you went through the test 1 memo, you realize that the table number or picture number, wherever that you get information out, are important. Okay, HFG, we go to the, if we go to the table, the value will be 10 to the power of 3 kilogram, and row is 0.05 kg cubic meter. Okay, so that's fine. How about reading the rest of properties? Reading the rest of properties. Properties at liquid water. Sorry, at film temperature. What is the film temperature here? So we know that Tsat is 40, but what is TS, like surface temperature here? The water, the input or inlet temperature is 25, outlet temperature is 35, so TS here is T bulk. .30, so T film will be 40 plus 30 divided by 2 is 35 degrees. Okay, we go to table A9, and at 35 degrees we find some properties and we write it down here. L is 994 kg cubic meter, UL 0.72, 0 10 to the power of minus 3 kilogram per second. Nu L, we know that it's divided by, but you can read that from the table as well. 10 to the power of minus 6. CPL, its capacity, we read that as well. Kelvin. KL. Units, don't forget about the units. Units are important. Watt, Kelvin, and Prandtl is 4.83. Okay, so we read all the properties. We might not need all of them, but when we went through the table, we just like write it down to see how we can use it. If you remember, like for normal condensation questions, immediately we would calculate the HFG star because we needed to find the condensation heat transfer coefficient. So HFG star was equal to HFG plus 0.68 CPL Tsat minus Ts. I mentioned here that it's a bulk temperature that is like 30, so we have all the numbers. 2407, 10 to the power of, we have it here, the power of 3 kilogram plus 0.68 multiplied by 4178 in joule kilogram Kelvin multiplied by 10 centigrade or Kelvin and HFG star will be equal to 2435 10 to the power of 3 kilogram. Okay, now we have HFG. So what was the next step? Okay, find the right correlation for finding the condensation heat transfer coefficient. So H horizontal is 0.729. There is like a correlation. You know that you don't need to memorize any of these ones, just like you need to go to your textbook and find the right one. G star plus KL, divided by L T sat minus TS multiplied by D. Okay, we have this correlation. Gravity, we have it. Well, we have it, we calculate it, we have it from the table. T sat 40, Ts bulk temperature 30, D we have it. So if we put all those numbers into the correlation, the final answer will be 11,775 watt Kelvin. Okay, we calculated the condensation heat transfer coefficient. But if we go back to the question, it's not asking us for the rate of condensation. It's asking for it's asking for rate of the condensation, but it's not asking for the condensation heat transfer coefficient. So what is asking us basically is asking for Q dot condensation, is asking for U, which is the overall heat transfer coefficient, and is asking for L, tube length, so 3. Okay, so now okay, all this calculation that we did was wrong. No, nothing was wrong, but we just a little bit jumped into conclusion a little bit early. Why? Because it was really tempting. It was very look like very standard question of condensation, like just go find the T-sat, immediately go and read HFG and rho at T-sat, go and read the rest of the properties at film temperature, so everything is fine, find the HFG star, and after that find the right correlation for H and you will be sorted. No. Okay, it's a trap. The same thing that might happen to you for boiling as well. Why? Because we mentioned that okay, looks like boiling, immediately calculate the delta T excess. Based on the delta T excess, it's very simple. Go and find what boiling regime we are talking. Go and find the correlation related to it, and go to the table, read the properties, and after that put it into correlation. Everything will be sorted. But here needs a little bit of like another kind of mentality and thinking. For example, here we want to say that okay, we want to find the Q dot condensation. How we can see it? Okay, Q dot of condensation is equal to Q dot of cooling water. Am I right? Yes, because Q dot condensation is equal to Q dot the cooling water. So if I want to calculate that, the only thing that I need to find is to find the Q dot of cooling water. How can I find that one? So we know that is m dot Cp T out minus T in. M dot of water, the cooling water, we know that we can find that m dot water is equal to rho this is velocity AC. Okay, so looks very simple. So let's find it. M dot of water, we can say that. Okay, so what is the like a density? So density of liquid 994, so we just write it here, 994. We read it at 35 degrees. Okay, multiply by 2 meters per second, multiply by pi 0.03 power of 2 divided by 4. Looks very simple, but now we just like find the m dot, but there is something wrong here. This one. Why? That's the reason I told you we just like jumped a little bit early into the conclusion. This is, we read it at 35 degrees, but now we are talking about a tube that water comes in at 25 degrees and goes out at 35 degrees. What's the right temperature for this system when we are reading any kind of like a property? The right temperature is 30 degrees. Okay, so m dot of water is 2 multiplied by pi 0.03 to the power of 2 O L at 30 degrees, which is equal to 996. It will be equal to 1.408 per second. The same when we want to calculate the Q dot. We said that is m dot Cp T out minus T in. We are just calculating for the cooling water. So again, the Cp should be read at 30 degrees. So if we put all those numbers, the Q dot will be equal to 58,830 watt. So what is this Q dot? Is the rate of condensation as well as the heat transfer rate and the rate of cooling water. Okay, so this example clearly shows that we shouldn't just like by seeing condensation or boiling immediately try to do the things that we were doing for like standard questions. Maybe a little bit of thinking and seeing if there is another way or what is the right way to calculate what the question is asking us. But in this specific case, we didn't waste our times, because at the end we can see that we really needed to calculate this H horizontal or condensation heat transfer coefficient. But in this case, you need to be really careful. Okay, the second section you see that is asking you to calculate the overall heat transfer coefficient. I said that you can remember that this overall heat transfer coefficient concept is related to heat exchangers, and if I'm not mistaken, this one was the easiest way of or correlation to write it with neglecting all the thermal resistances. So basically we need to find two heat transfer coefficients, heat transfer coefficient the outside and inside. So it's clearly shows that the outside heat transfer coefficient is the condensation heat transfer coefficient, and inside is the average heat transfer coefficient for flow inside the tube. So now, thanks God, it's good we didn't like lose any time, so we already did the calculations, but we had to do it in the second step, not the first step. Okay, otherwise we would have lost lots of time if the question was just asking the rate of condensation. Okay, so let me just write it here. Seven 11,775 units. Don't forget the average heat transfer coefficient. Now, okay, average heat transfer coefficient, internal flow. You are completely familiar with this concept. First, you calculate the Reynolds. From the Reynolds, you go and you find the right correlation for Nusselt's number. You calculate the Nusselt's number, and after that, based on the Nusselt's number, you go and you find H. Okay, so let's do it. It looks very, very simple. So Reynolds, Nusselt, H. So Reynolds, we know that we can just like average the, so if we go back, we calculated this one, but again we calculated that at 35 degrees, but here we are just talking about heat exchangers part, or this part basically. Going in 25, going out 35. So if we go to the same table and read the property at 30 degrees, we are having 0.801 10 to the power of -6. The velocity, we have it 2 meters per second. Diameter, we have it 0.03 meters. So Reynolds, we can find it is 74,906. Okay, if you go to the to your textbook, you can find the right Nusselt's number for this Reynolds, or the right correlation to calculate the Nusselt number is 0.023, Reynolds to the power of 0.8, and Prandtl to the power of 0.4. Again, Prandtl here should be read at 30 degrees. If you go to the same table and read it at a different temperature, the Prandtl will be 5.42. So now we have the Prandtl, we have the Reynolds. If we put into this correlation, the Nusselt will be 358.9. Now we have the Nusselt's number, so we can find H. H will be Nusselt, KD. Nusselt, we have it, D, we have it. How about K? Again, we can read it at the table at 30 degrees. So it will be 0.615 Kelvin, and HI will be equal to 7357 watt Kelvin. We have the average heat transfer coefficient. We have condensation heat transfer coefficient. So it's very easy to find the overall heat transfer coefficient. U will be equal to 4528, but just like keep in mind that this unit is exactly the same as this one, so there is absolutely no difference between these two. So that's the combination of different concepts that I was talking. Here we said that okay, we are familiar with the concept of overall heat transfer coefficient. We know that neglecting all the thermal resistances, easily we can say that it's like internal or average heat transfer coefficient plus condensation heat transfer coefficient. This one we could find it from the chapter of the textbook related to internal flow. Very simply, first calculating Reynolds by properties at the bulk temperature, inlet plus outlet divided by 2. After that, finding the right correlation for Nusselt number based on the Reynolds number. Finding the Prandtl from the table at again the bulk temperature, and finding the heat transfer coefficient. But for HO, or condensation heat transfer coefficient, or heat transfer coefficient on the outside of the tube, so of course it was a condensation question and we had to solve it to find the condensation heat transfer coefficient. So you see that now we basically combined two different concepts of heat transfer. But we are not that lucky. We are not done, because the question is asking L as well. Okay, so our job is not done. Let me think about it. How we are going to calculate L? It's okay. Let me think. Any ideas? If you remember from the same concept that we said about heat exchangers, we remember that we were calculating the overall heat transfer coefficient for this correlation, to use it with this correlation. Otherwise, we were not interested in calculating the overall heat transfer coefficient. We used to calculate overall heat transfer coefficient to be able to use this correlation. Okay, the logarithmic mean temperature difference here, logarithmic mean temperature difference. But okay, we have it. We have the overall heat transfer coefficient, Q dot. We have it. Condensation rate, heat transfer, condensation heat transfer rate, or the only thing that we need to find is like AS as well as logarithmic mean temperature. But here it's like we were looking for L. How about AS? You remember what was AS? It's a little bit different from the AC. So it's like a surface, like a if you remember, we can find it with a very simple correlation of pi dl. So basically now we know that L can be calculated from this correlation. we have this one, we have this one, we have this one, we have this. The only thing that we need to find is the logarithmic mean temperature difference. So basically it will be 15 minus 5. 15 divided by 5 is 9.02, and finally L will be equal to 15.1 meter. Here how we find it, so basically it's 40 minus 25 and 40 minus 35. This was 15, this was 5, and after that we put it here. Okay, so basically that's it. We find the L question was asking us 15.1 meter. We also could find the overall heat transfer coefficient that the question was asking, and as well as condensation heat transfer rate, or yeah. But there is a very important thing to keep in mind, that when you see these kind of equations that at the beginning look very simple in terms of you see the temperature saturation temperature, and it's really tempting because it's very easy to get into the trap that, okay, I have the saturation temperature, so let me just go through the table, read all the things, and I will be fine. No, it's better to first think. In this case, nothing happened to us. We went to the table, we calculated the condensation heat transfer coefficient, and after that we used it. But sometimes, because that's a reason that the majority of students at the end of the exam or test, they say that you know what, the time was not enough, because those kind of timings are set by university, and at the same time when we send the exams to the external examiners, they evaluate the quality of the paper as well as the time. So they recommend that, for example, the questions are easy or hard, or there is a form that they need to fill it, but at the same time they think about if students can write the answer in the time that we are giving to them. So time is important for external examiners as well. So don't worry about it. Any kind of test that you write, you can be 100% sure that we thought about timing. We spoke with external examiners about it. But of course, if you need extra time and you are one of those students that university is giving you extra time, you can just apply for it, and after that send me the confirmation. I hope you learn something by solving this example together. Please do it one more time by yourself. Try to go and find some kind of, another example from your textbook or other textbooks, and see if you can combine different concepts that you learn into each other, and see if you can answer it. In this case, it was the first section was very easy, but for the second section we realized that we need to find two heat transfer coefficients, internal and external or outside. And outside we knew that it is a condensation heat transfer coefficient. So all the information that we read from the table at the beginning was okay, we used it. But it's better to first start step by step. First answer what the question is asking, after that the second part, the third part, because those are related to each other. So that's it for today, and enjoy the rest of your day.